All right, as I said, welcome back to System Software. So today we're going to be continuing with our toy compiler, and we're going to look at some tools that we can use to help generate parts of the compiler for us automatically. But first I'd like to see if anyone has questions about the toy compiler last week. So last week we looked at this very simple compiler that would take just a text file that had the symbols of arithmetic operations, translate them into Intel assembly, and then we could actually compile and run that on our x86 hardware. Questions about that process last week? Okay, so just to review quickly, we had three phases. We had lexing, parsing, and code generation. And what did the lexing phase do? What was that? What did that accomplish for our compiler? Any takers? Yeah.
The lexer converts like strings and regular words that have no input tokens.
Yeah, exactly. It tokenizes the input. It takes groups of ASCII characters and groups them together into the words of our language, or the symbols, the names of the symbols of our language. So in our toy compiler, what symbols did we have? What tokens did we have in our toy compiler language? Yeah.
Numbers and operators and then the semicolon.
Yeah, numbers, operator, semicolon, and there was also an end of file token that we had. All right, good. So the next phase after that, then we had all the words. I can actually show the terrible handwriting from last time. And then the next phase was parsing. What did the parsing phase do? What was its input? What was its output? What was its purpose? Who'd like to answer? Yeah.
The reason the tokens that it tells like what that actually does.
Tells you what it does? Okay, so it does something with meaning, yeah. More concretely, what is its output? What is the output of the parser? Yeah. It does output a list, so statement lists are a list. Yeah. Yeah, outputs the hierarchy. So that we represent that with a tree. So we've all learned trees in CS1, CS2. The tree is the data structure that the parser produces. And to your fellow students' point about what it does or what it means, there is this kind of relationship between syntax and semantics, kind of philosophically. You know, in some sense, by determining the syntax, if you can figure out that this is an expression, or this is a noun phrase, or this is a verb, it does provide some indication about what the purpose of that is in the language. The parser has a little bit of a more modest goal. It just tries to identify the legal groupings of words in your language. So for instance, the lexer will tell us which tokens there are in the input, but the lexer doesn't, just identifying the words in the language, doesn't rule out expressions like this. If I said 1, 2 plus, this may be a valid utterance in some language, but in our toy compiler language, it's meaningless. Even though these tokens are real words in the language, this specific arrangement of them is meaningless. So there's this classic notion in linguistics, or this classic kind of phrase, colorless green ideas sleep furiously. This is Noam Chomsky's seminal work on syntax and semantics. And the observation here is that this sentence is designed to be meaningless. I mean, you could probably make up some meaning to it. But the point is, if you have a sentence like this, colorless green ideas sleep furiously, there's something different about that when you compare it to a different arrangement of words. Furiously, sleep, ideas, green, colorless. Anyone notice a difference between these two? What is the difference? Yeah.
One has like correct adjective order, and it works grammatically.
Yeah, one just seems right grammatically. When you hear this, regardless of whether you know what it means, It feels like a real sentence, whereas the second one doesn't. And this illustrates the crux of what syntax is as separate from semantics or word identification. And this sentence diagramming is exactly what our parser is doing. The lexer just tells us that, hey, these are words in our language, and it identifies them for you. The parser figures out whether there are valid arrangements of words. And so if you just take the whole set of all possible arrangements of words in our, say, toy compiler language, there's lots of different ways to order the words. You could have a million nums, one after another. It's the parser and our syntax specification that allows us to specify which arrangements of those words are legal. And beyond that, these arrangements of words, we assign them names, we assign them symbols, which do map to meaning. So in our toy compiler language, we mapped these arrangements of words in our language like expression. We said an expression can be recognized by seeing a num word followed by an op word or token followed by a num word. And because we can identify that as an expression, we can ascribe meaning to it. And so that brings us to our third phase. What did code generation do? Once we have the words in our language identified, and we have the syntactic structure, that is the legal arrangements of words and the names of those arrangements, like expression or sentence, then we could do code generation. And so what was the input and output of our code generation? Or what did it do? Yeah.
The code gen took this abstract tree of expressions, the statements, and converted it into our output language, that is readable in assembly.
Right, so it took, yeah, exactly right. So it took this tree, this syntax tree, and it generated Intel assembly. And so our code generator is really just a translator between two languages. It takes this syntax tree, which it uses to represent the structure of the input language, and it takes each one of these symbols in our input language. So this symbol doesn't appear anywhere in the actual input file. There's nothing in the input file that says, hey, I'm telling you an expression right now. Instead, we can infer when something is an expression in our input language by looking at the arrangement of tokens. And our code generation, by inferring which syntactic structure was being used in the input, it could map the meaning of that to a different language. And so in some sense, our code generator is a definition of the toy compiler language. It's defining the meaning of it in terms of another language. So for instance, if you didn't speak Chinese, somebody could translate that into English, if you spoke English, and you would understand what they meant. And we just assume, if that translation is correct, that you're going to get the exact same meaning. And it's the same thing here. We have this toy compiler language, which I just made up for you, but it kind of is based on the math language that you all know. And we, on our code generator, translated that, defined the meaning of it by translating it into another language that we also, has some definition to it. Questions about this? At its core, this really is the job of a compiler. It is translating between two languages. And the tricky part is that we as humans, we learn language and we kind of transparently use it every day. We don't think about how we understand what 4*1 means. We don't think about the fact that they're just symbols. And for instance, if you were speaking Chinese, you may see different characters here. You may see characters that you don't recognize. And that's the same thing the machine has to deal with. The machine has to deal with symbols that are just ASCII numbers. They don't have any actual meaning. It's the compiler that ascribes meaning to them. All right, questions about the toy compiler? So quick little quiz. We translated it into Intel assembly. What defines the meaning of Intel assembly? Or who defines it? Or where does that get handled? So again, it's just another representation. Yeah?
I guess Intel defines the meaning of it.
Intel defines it. And the processor itself actually interprets the meaning of those symbols. So if you remember from computer organization, You just have opcodes, which are just numbers mapped to an operation, and the hardware takes those opcodes, takes in your registers or immediate values, and gives you some output. And sure, so Intel defined the meaning of that, or AMD, for Intel for x86 64. All right, good. Questions? Questions? Thoughts on the compiler? Okay, so that's, so today I'm going to give some more techniques that we can use to process the input language. And then we're going to go over the actual language we're going to be compiling this semester. Okay, so let me give a quick review of the phases of the compiler that we just went through. So in our toy compiler, what was the first phase? The lexer, good. So we had the lexer. The lexer turned ASCII characters into tokens. And what was the next phase? The parser. The parser turned our sequence of tokens into a parse tree. And then our last phase was code gen. And this produced our assembly. In the toy compiler, we had a C file for each one of these. Now, writing a lexer, something that's going to tokenize ASCII for this very simple language, is not too bad. But once we start getting into a larger language, like C or Java, where there's lots of words in the language, there's lots of keywords, there's lots of operators, it can be useful to not just write code that's going to try to tokenize this, but to actually specify what the tokens in our language is. And so who's used regular expressions before? Not too, okay, a little bit. So regular expressions are a way to define tokens. They're a way to define sequences of characters. And so one of the first tools we're going to use when building our real compiler is a tool to automatically generate the lexer for us. So we're going to use a tool called Flex, but it's really just a tool that will take, so this is the name of the tool. And what it does is it takes regular expressions and it translates them into a lexer. And so one term that people use to call these kinds of tools that generate parts of the compiler, they call them compiler compilers. Because what Flex really does is it takes a specification in one language, in this case not a programming language, but a specification of the tokens in your language, and it translates them into code. And so I'll show what the specification actually looks like, but it's a little bit easier to read and a little bit easier to make sure it's correct to just specify a pattern of what tokens you want in your language, and then just have a tool that will automatically translate them for you into your lexer. So you won't have to handwrite your lexer. And in fact, I've given you the token specification as well. Okay, so that's the first compiler tool that we're going to be using. And the second one is a parser generator. So again, in our toy compiler, we had a very simple language. There was only 3 constructs that we had to parse. But in C and other languages that are structural and they have nested constructs, it's a lot more complicated to write parsers that are correct for these languages. And so the parser generator will take a syntax specification and it'll automatically translate that into code that will parse or recognize that input. And so these actually do make the job of writing the front end of the compiler easier, but they are their own languages themselves, and so we have to learn how to actually use those languages and how to actually use them to do something like build a parse tree or generate code. Okay, so that's what we're going to go over today. We're going to go over a new version of the toy compiler that replaces these components, the lexer and the parser, with specifications of the lexer and the parser. And we're going to use these tools, which you can find, they're old tools. They're free and available for everyone to use. They're automatically installed in your regular machine to generate this front-end part of our toy compiler. And the reason I'm doing this for the toy compiler and having you do this again is that we're going to be using these when we get to our real compiler, and I'd like to have a little practice using them because they have, they have their own syntax, they have their own language. They have to learn their language a little bit. Okay, questions? Questions? Yeah.
Sorry, I'm just,
Sure.
what's the word to the right of syntax in the box?
Oh, here. Sorry. This is Bison. Yeah, I should probably do text boxes instead. Yeah, this is Bison. So it's the name of a tool. It comes from a very nerdy computer science joke of the previous version of this was called Yak, yet another compiler. And a yak is somehow related to Bison, so the new version of Yak became Bison. Other questions? Any questions on this? Yeah.
What is ASM?
Assembly. Sorry, yeah, that's the output of the code generator. Questions? Other questions? So, but it's just taking this classic phases of the compiler and having tools that will generate parts of these phases for us. That's why they call them compilers. If you could have a way to specify your language and then automatically generate a compiler for it, that would be a useful thing. Okay, so I already went through our previous toy compiler definition. I already went through this already, actually. So, the idea here is that we just specify the input language and then generate code that will translate it. So in the same way that you specify a program in C, and then you have a generator that will turn that into assembly language for you, so you don't have to do assembly programming. Similar idea here, where we specify the language. Okay. So let's take a look concretely. All right, let me do this here. Okay, I think that's easier to read. So who's finished their first toy compiler exercise? Okay, some people. So hopefully if you've looked at it, this might look familiar. This was the lexer in the first project. You can see here it's code. It's code that if you want to figure out what it was doing, you'd have to read the code and try to infer which tokens it's processing. In comparison, if we use this regular expression, this language for specifying tokens, we can be a lot more parsimonious and declarative in how we define what the tokens in our language are. So these are the three sets of tokens that we have in our language: number, semicolon, and operator. And the way this flex specification works is on the left-hand side, we have this pattern that specifies what strings match this token. And so all this regular expression says is any single character between 0 and 9 is a number in our language. And for keywords and symbols, it's very simple. Instead of trying to do any sort of matching or looping over, iterating over a sequence of characters, we can just specify a raw string and just say, whenever you see this string, return the semicolon token for us. And similarly for operators. In the regular expression world, this pipe symbol, this vertical bar, means or alternative. So if you've taken discrete, this might look familiar. But all this regular expression is saying that any one of these 4 characters matches an operator. So comparing these two, for this language, it's not that much different. The size is certainly a lot smaller. It's a lot easier to see that any 4 of these tokens all represent the same, or any 4 of these characters all represent the same token. And so you can imagine as we get to a larger language like C or Java, where there's a lot more possible tokens in the language, having a specification like this where it's very clear on the left exactly which string patterns match what words in our language, it's a lot easier to do this correctly. And then you don't have to do any kind of debugging in your C code as long as your lexer generator works correctly. Questions on this? And so yeah, if you've worked with regular expressions, this may look familiar. And we'll go over regular expressions more in, I think, next week or in 2 weeks. Okay, so that's testing. Oh, still works. Okay, so that's the lexer. If you're curious and you want to read about this tool, this is the documentation is in the notes. Okay, so let's compare the parser with the parser generator specification. So here was the code. Oh, sorry. So here was the code for our parser generator. And so we only had 3 constructs in our language. We had a statement list, a statement, and an expression. And if you remember last time I went through these comments here, I put comments here to kind of write the schematic of what this parser function is doing. And what it's doing is it's recognizing an expression as being this particular sequence of symbols in our input language. And in order to actually implement that, we had to do all of this reading of tokens, checking one at a time, constructing the AST. And what the parser generator allows us to do is take effectively this comment and just tell the parser generator, hey, this is a construct in my language. I want you to just recognize this for me. So here is what that looks like in the parser generator's input language. So you can see here, I can literally just say an expression is, this colon just means like an equal sign, is number token followed by an operator token followed by a number token. Can ignore the stuff inside of the curly braces for a second. This is code that will be executed once you match the input. But this allows us to just turn, instead of having to write this complex recursive set of functions, all we have to do is specify the grammar constructs in our language using symbols. So here's the expression, number followed by operator followed by number. A statement is an expression followed by a semicolon. A statement list is either nothing or it's a statement followed by another statement list. So remember last time in our first toy compiler, we effectively read the input by traversing a linked list. This is the kind of grammatical specification of that. By having 2 options to match statement list, we can recognize an arbitrarily long list, statement followed by another statement list, which is a statement followed by another statement list. But whenever that list is done in the input, we can also match just the empty input. Matching empty input is probably a little hard to wrap your head around. How do you match nothing? And when we get into parser generated and how it works, we'll see the kind of magic that goes into making that possible. But basically, if we see nothing in the input and it doesn't match anything else, the parser that this generates can actually recognize that, oh, we've actually seen a complete statement list. If there's nothing else that is allowed to be empty in the language, and this is it, and there's nothing else that can match, then it can deduce that you must have seen an empty statement list. And I just gave also, I think that I've programmed here. I think I did this just to have a single top node for this language. Questions on this specification? Probably a lot looks unfamiliar. Questions about the idea behind it? Okay. All right. So the way this works is this language specification, this grammar specification is given to this tool, Bison, and it'll generate a program, a C program. Probably won't look like this, but it'll generate C code that you can then compile and execute. But the utility of this is that not only will it recognize the input language, but you can also give it code to run once it recognizes a grammar construct. So this code in curly braces will run after the parser recognizes the input language. In our toy compiler, we kind of did this manually. So this parse expression recognized that we had a number followed by an operator followed by a number, reading in the next token, doing all the grunt work of processing the input. And then once it recognized that, yes, we have this valid statement, it generated a create expression parse tree node. And so this is the code that goes into this, what's called a semantic action. So whenever we recognize a part of the input, we can tell this Bison tool, please run this code for us. So this, you can think of this as just a more parsimonious way of saying this function here. Recognize those tokens in the input for me, and then run this code. This double money sign is basically the same thing as saying return. Whenever we, just like here, we returned an expression node so that the caller would create that as its child node. So just as a refresher on our parse tree. As soon as our parser recognized that we had an expression, it created a node and then passed that to the function that called it. The function that called it was the statement parser. So the statement parser recognized when we saw a statement by saying, okay, tell me if you see an expression. The expression parser recursively checks whether it sees the sequence of tokens necessary for an expression, and then constructs this parse tree node. Once it constructs that parse tree node, it passes it back to the statement parser, which had originally called it. That was how this parser worked in the first version of the toy compiler. And we can express all that without dealing with C code or dealing with reading in tokens or checking whether they match a specific token. We can express that in our Bison syntax specification with this code. All we have to say is the grammar construct. An expression is number followed by operator followed by number. And then tell Bison what code we want to run once we've seen that expression. These money sign variables, yeah.
So we're writing this code, and then Bison takes it in and generates the C code?
That's right. Yeah.
Coming off of that, the output of the Bison replace the parser code from the compiler.
That's right. It'll replace it, yeah. And so in the new toy compiler exercise that I've given you, there's no more parser.c. Instead, you've got this parser.y file, which is the extension for bison or yak. You have this file. So just to show what that looks like, here's the, well, maybe it's better to show, well, yeah. I should probably show it on GitHub. So there's no more lexer.c and there's no more parser.c. These are replaced with parser.y and lexer.y. And I'll show you in a little bit how we manage this project, how we manage the generation of the code and linking of the code. But yeah, you're exactly right. So there's no more lexer.c, there's no more parser.c. These are replaced by our specifications of what those programs should do. And so generally in software engineering, this is a good practice in general to, like what I talked about in the first day of class, is the kind of one way to reduce the job of software engineering is to take a specification and create its implementation. And it's very easy, when we're kind of thinking about the technique of programming to just think about implementation. But as I talked about in the first class, putting the specification first and thinking about how you divide and conquer that specification in order to do your implementation can make much safer and faster code creation. And this is an example of not just having a specification of your program, but having a mechanically readable specification. And so there are actually efforts in the research world to not even have to implement code, you just specify it. So there are formal ways to do this, there are statistical ways to do this. But have in your mind when you're writing code, what's the specification, a detailed specification of what the program is supposed to do. That'll make it much easier to have an implementation, and you might even be able to generate code that will do that for you instead of trying to write the code. Yeah.
So when you compile this file, for example,
Yeah.
the output be a C file?
Exactly. Yeah. The output of this is a C file. So here is the output. It's not going to be fun to look at, but this giant C file is the output of the output. So I can actually show you. There's basically, so YYLex is reading in one of the inputs, and so this function here, I think, is the parser function. So it effectively, So this is the parser function here, and it looks really long. We'll get into a couple weeks how the parsing actually works. It doesn't use a recursive set of functions, which is called a recursive descent parser. Instead, it uses a state machine to do this. And we'll talk about state machines and this stuff in a couple of weeks. But this is the output. It literally generates a C text, generates the text of a C program when you call Bison on this file here. So this little, comparatively little file becomes this pretty large C file. And so this code here, this is actually part of the, I think, state table for the state machine. But yeah, good question. It actually, it literally generates C code. Yeah?
In the parser.y file, you write the symbols in like a hierarchical order, starting at like the top. Is there a specific reason? What would happen if you...
That's a good question. So does the order of the symbols matter? And so, strictly speaking, no. There's only one symbol that matters, the starting symbol. This is, I think even in Bison, the first symbol is the starting symbol. Actually, you might be able to specify it differently. I think by default, so we actually specify the starting symbol. So actually, no, the order doesn't matter in a Bison file. When you're looking in, if you're in like discrete or looking at like about formal grammars, the starting symbol is usually the first one. It's part of the definition of the language, so you have to say, here's my starting symbol. So strictly speaking, no, the order doesn't matter. As long as you know what the starting symbol is, that's all you need to know about the ordering of the grammar. So why is that? Why is it that the order, how can we figure out the order, even if...
just by looking at the sub-objects reference.
Exactly, yeah, you can look at what each symbol expands to. So this expands to a statement list, so you know that statement list is underneath program. So it wouldn't really matter if we reordered these in the input. But to Bison, I think also, Bison doesn't matter for Bison either, because you tell it what the top symbol is in the specification. Questions on this? Yeah.
So, because it kind of implicitly is a hierarchy in which function falls, even though the order doesn't matter.
Yeah, exactly right. Yeah, that's a good way to think of it, is that if you think of each of these as a function, just like in our handwritten C parser, our parser for written in C, the way I designed this was to have one function for each grammar construct. And you don't strictly have to do that. I mean, if you look at the parser that Bison generates, it's just a giant loop, basically. It uses a different technique for parsing. It uses a state machine. But organizing these into one function per grammar construct allows us to see and represent this grammar construct more easily. And so you can think of this specification as being a set of function definitions. So you can think of this as the function name and this as the function body. In the same way that, so for instance, for expression is the function name because it's the name of the symbol that we're trying to recognize. And the right-hand side is the sequence of symbols that make up that construct, and you can think of that as the body. Think of that as the body of the function. So looking again at the function that we wrote to recognize this expression, that's exactly what we did. We had a function that was called expression, and we, one by one, read each symbol that is supposed to appear inside of that expression. And so notice that for statement, if we have another symbol that's not a token in the language, we have another grammar construct. The way we designed this was we just called the function that recognizes that symbol. So this gives us this nice clean organization of the processing of our language, where each construct is recognized with a single function. And when we want to recognize nested constructs, like statement, we just call the function that recognizes that nested construct. Questions? Yeah? No, they're different languages. So Flex, so that there's kind of an interesting question there, is that you could, so grammars are strictly, these are context-free grammars. They're strictly a superset of the languages you can recognize with regular expressions. So technically speaking, one subsumes the other, but they're represented differently. So the way they're represented is different. And we'll talk about that more in a couple weeks when we get into the details of these. But they are different languages. So one is using this regular expression operators like or and concatenation, and the other is using this grammar specification language, which we'll get into the formalities of that. So even if you don't care about compilers or not interested in implementing compilers, most people will not have to do this or even want to do this, most likely. There are a few useful concepts for software engineering here. One is not just having specifications, but having specifications that are machine readable that can save you the work of doing coding. So if you can express what you want to do, not just in words, but in a precise formal specification, then you can actually just write code to generate code for you. So this is like that kind of classic programmer meme that a programmer spent 2 weeks automating something he could have done in like an hour, right? Everybody hear that joke? Like there's an XKCD comic about it. But when you're doing larger projects, like a big complicated piece of software like a compiler, being able to not just specify what your code is supposed to do, but specify it in a machine readable and automatable way, you can instead think about how you can generate code to solve your problem. Yeah. You mean like a tree? So this is a context-free, this is basically a context-free grammar.
I just mean like, you know, how formula is
Oh, I think they're called syntax diagrams, is that right?
I mean, I just have a picture of it.
Yeah, show me during the break, because I think they're like syntax diagrams, I think, right?
There's like terminal variable, certain terminal symbols and then variable.
Is it something like this?
More like,
Yeah, it's just yeah. So what he's showing is the sort of mathy way to write context-free grammars. So this is called Chomsky normal form, I think. It's just another way to, it's just another set of symbols. So instead of colon to say this grammar construct is, can be decomposed into these symbols, there's an arrow. But I'll go over that when I get into the formal grammars. There's no arrow like ASCII character, so I'm guessing that's why they used colon. But this is the same thing as saying, you know, if you had P, you could do it like this, for instance. But we'll get into the formal stuff. But it's the same, it's equivalent. And so it's like a one-to-one mapping between those languages. You could write a little translator or transpiler between those. The other aspect of software engineering that I hope you'll take away from this is using functions and breaking up your specification also in a machine-readable way, using functions or other abstractions in the language to break off pieces of your project in a way that will make it easier to just reason about that one piece. And in the world of parsers and compilers, you have to be really careful about how these work together. So this statement function has a really specific specification. It recognizes whether you've seen a statement, and then it returns a tree node. And and then that means the parent, the statement list, has a guarantee that whenever it calls statement, there's either going to be a parse error or it's going to get the child node that it needs. So there's two kind of takeaways here. Is that one, try to make your specifications mechanical and machine readable, because then you can actually translate them into code if you want, or at least you have something unambiguous to express to other developers, other users. And you can break down your specification in such a way that if it's really precisely defined, you can these functions can combine together, can compose together into a single program that does exactly what you want it to do. But anyway, we're going to see this in the context of compilers. And this grammar specification language just gives you a way to not have to deal with some of the details of parsing, but also be able to run code whenever you see one of these grammar constructs. Questions? Questions about this? Yeah.
What exact is $.node?
Say again?
What exact is $.node?
Oh, okay. So yeah, that's actually what I was going to go into next, is what does this mean? What does this code mean here? Okay. So as I mentioned before, these parser functions first recognize the input. They first check, do we see an expression, and then do we see a semicolon right after it? If we do, then we know we've seen a statement. But that's just checking that the input matches our grammar. The next thing we do in order to create a tree for our code generator is to create one node of that parse tree. So recall in our grammar tree example here that the goal of our parser was each of these parsing functions created one grammar node, and we called these in this recursive fashion so that the child call would produce a node that the parent call can use for its tree. So we kind of gradually, recursively built up this tree. The expression just took the tokens, created a tree node out of it. This tree node was passed to the caller, which was statement. Statement took that expression and the semicolon, constructed a tree out of it, if we were making a parse tree, and so on. Statement list took the completed statement node and used it to construct its own tree. That's what this code is doing. Every time we recognize one of the input constructs, we create a tree node and pass it to the parent. And so the parent will continue building up this tree, bottom up. In order to do that with our parser generator doesn't actually do, technically it doesn't do parsing, it just does recognizing. Recognizing is checking whether the input language has a grammatically correct sequence of tokens. In order to do parsing, that is create a tree out of it, we have to tell Bison what code we'd like to run whenever we recognize one construct in this language. And so it gives us this kind of special symbols that we can use in our code. So strictly speaking, you could put any C code here. This code literally gets copied into the output parser. So here's our output parser. And I just searched for create statement. So here is literally where the parser generator copied the code in the braces into its output generator. So the case statements, this is where it's has successfully recognized one of those grammar constructs. But this code here is literally a copy of what we wrote in the Bison parser generator, except for these special symbols that Bison lets you set. So these are like placeholders for something in the output parser. So this doesn't give us a whole lot of info to go on of what these mean. So let me explain to you in the context of our original parser what these mean. You can think of this as the return value of this parsing function. So in our first toy compiler, we recognized the input, generated a tree node, and returned it. This double money sign is Bison's way of saying, this is the value I want you to return once you recognize this grammar construct. And by the same token, I guess pun intended, money sign 1, 2, 3, 4, etc., these represent the return values of the nested function calls. So let me show our original parser. So here, every time we recognized another symbol in the right-hand side of our grammar construct, so here we got the next token, put it in operand 1, we got the next token after that, put it into the operator variable, got the next token, put it into operand 2. And then when we constructed our expression, we constructed it out of those 3 child nodes. Similarly, in parse statement, we recursively called expression, got the node that it created, and created our new statement node using expression as the child. This is a schematic way of saying that same thing. Where, so for instance, for expression, this is the return value, and each of these represents the nested return values of each symbol on the left-hand side, or the right-hand side of our grammar production. So number 1 is whatever the return value of calling number is. Number 2, money sign 2, is whatever the return value of calling operator was. Money sign 3 was whatever the return value of calling number was. The same thing with create statement. This is saying, here's the value I want you to return after you recognize a complete statement. I want you to call this create statement function and pass in whatever the return value you got from the first symbol on the right-hand side. So money sign 1 is whatever the value that calling and recognizing expression produced. Questions on that? Kind of makes sense? Questions? Sort of makes sense. Sort of. So it's another way to kind of express this recursive behavior of our handwritten parser. Yeah.
Statement, what is this semicolon? Like,
So that's a good question. You notice here, we're only getting the value of the first symbol, but the second symbol, which would be represented with money sign 2, isn't being used. And so it turns out that there are symbols in the language that don't have any use in our parse tree. So the reason for that is once we've created a statement node, one way to think of it is that every single statement has a semicolon symbol in it. And so it's basically redundant to add the semicolon. You could add the semicolon to it, for sure. But what we're creating here, we could call an abstract syntax tree. That is, it doesn't capture all of the input tokens, but just enough in order to recognize what grammar constructs that we've seen. So we'll talk about that more, I think, next time, syntax trees, when you go to actually do this for the real compiler. But basically, there are symbols in our input language that have little use beyond helping you parse the language, helping you disambiguate the language. So for instance, in kind of, whoops. If we think about just like math expressions that we learn, say in grade school, what does the parentheses mean? Are the parentheses an operator in the language? What do the parentheses do? Yeah, they change order of operations, right? They change order of operations. So if I just said like, 1 parenthesis 3, it's meaningless, right? There's no meaning to 1 parenthesis 3. So there's no mathematical operation that corresponds to parentheses. All it does is it tells you, the reader, that there's a change in the order of operations. But it itself doesn't actually have any mathematical meaning, in the sense that it doesn't do any operations on numbers. There's no mechanical operations on numbers. It just changes the order that you interpret the operations in. And so you can think of semicolons and parentheses in our languages as well as doing the same thing. They change how you should be parsing that input. So this tells you that you should be parsing this into a tree that does the plus operation first and then does the multiplication operation versus this one. So the meaning is different, the end meaning is different. But in terms of like the computational content, the parentheses doesn't actually do anything besides tell you to change the order of operations. So you can think of a semicolon as the same thing. It provides a way for the parser to unambiguously know that we've seen a complete statement. And there are languages these days that don't use semicolons, right? Python uses indentation to identify when you have a new statement. It's really just making the language unambiguous. And so once that purpose is done in the parser, it's redundant to hold on to it. Now there are reasons you'd want to hold all of the symbols in the parse tree. If you want to say print it out again, you can do pretty printing, or you can do source-to-source translation. But yeah, it's a good question. What is the semicolon? What's the semicolon there for? Questions? Yeah.
So in the line where it says statements in lists, to the right it says $1.92. That's referring back to statements.
That's right, yeah. So yeah, good question. So here, there are two possible choices for our grammar construct. So if you recall in our first toy compiler, the way we were able to parse an arbitrarily large input, any number of statements, one way to think of it is that there are two possible ways to identify a statement list. Either you see a statement followed by another statement list, which would be an infinite recursion, or you see nothing. So, I mean, this sort of kind of makes like intuitive sense. If you just see statement, then you see nothing, that you can use to interpret as being the end of the list. And we capture this by having two possible ways to match statement list. That's what these two lines are representing. We've got the second way to match a statement list, and it's you see a statement, and then you see another statement list following it. And this semantic action, this code, represents what you should do if you see that version of a statement list. We're telling the parser, call this create statement list function, pass in whatever the return value, the node for statement is, and then pass in whatever the node that you generated for statement list is. And then return that new node. Yeah.
So we still define the create functions, like those are.
Yeah, we still have those. Yeah, these are not given to us by Bison. These are still in the AST. So this other alternative, this is matching empty. So if we don't see any other input, in this case, then this is the production that matches that. So I just put this as a comment here because it can be, you literally just put no text besides spacing in order to match empty space in Bison. But it's good practice to put a comment so that you know it's meant to be empty, like this page intentionally left blank. And because it's a different pattern for matching, we have a different set of different code that we want to run whenever we match that. And here, all we do is set the return value to be null. This is going to have the same effect as our statement list parser here, where we're effectively just traversing a linked list and generating that linked list as we traverse it. Yeah.
So is that why it has like the or line?
This or?
Yeah. It's like else.
Yeah, exactly. You can think of this as like if else, where there are two possible branches. That's exactly right. So you can think of this as just a switch case or a long set of if then else statements. Yeah.
Can you explain again the green semicolon, like why don't you put like a dollar sign too?
So you could. So this is a design choice about what the output of our parser should be. So for our purposes, we're just going to traverse this list and generate Intel assembly. So because that's all we're doing, we certainly I could have designed the AST to include a slot to hold that semicolon. But this is more of a design decision. This is just keeping out information that we don't need for our purpose. So in order to translate this to assembly, we need to know when we have a statement. But the semicolon, because it's just used in the input like a parentheses to help disambiguate when one statement ends and another statement starts, we don't need it for translation. But if we wanted to be able to, say, rewrite the input, maybe, has anyone ever used a pretty printer? Or in their IDE, it'll automatically do indentation, or it'll make it'll follow some coding style guidelines. Those IDE tools will make a tree, and it'll keep all of the tokens from the input, including the semicolon. And so if your IDE, say, does automatic refactoring, or it'll pull out a function for you, or it'll do syntax highlighting, or pretty printing, it is making a tree that preserves all the input tokens. So there's nothing kind of fundamentally true here. This is really a design decision that I made for the syntax tree. And so the name for that is parse tree or concrete syntax tree, which has all of the symbols from the input, versus abstract syntax tree, which removes information that whatever the downstream phase of the compiler is going to do doesn't need that information. In practice, compilers may have both, if they have to do rewriting or if they're used for pretty printing. It really depends on the usage. So like I said in the first class, an abstraction is designed based on how it's going to be used. And so in this compiler, we're just using it for code generation. And so any symbols that we don't need for code generation, we can leave out. But it's just a design decision. There's nothing fundamentally true or right or wrong in keeping the semicolon in or not. Another way to look at it is that because a semicolon appears in every statement, the fact that we have a statement node actually tells us that a semicolon should be there. So we could still pretty print this by saying, if I see a statement node, just always print out a semicolon afterwards. But if there were several types of statements, some of them had semicolons, some didn't, we'd have to preserve that information somehow, either with a different type of node or by preserving the actual tokens from the input. But yeah, good question. Good question. Yeah.
What is the code generation part like called?
In this parser, it's identical. The code generator is the same in this compiler. Is that what you're asking?
Yeah, but like how do you get the statement list and then when you call the
Oh, so the main function is pretty similar. So the question was, how does this generated parse tree get used by the code generator, right? So it's not much different than with the original toy compiler. So let me compare the main functions here. So in our first compiler, we had this, our parser functions always returned. It like literally had a function return. And we could just save the pointer to that abstract syntax tree node and then pass it to our code generator. These are details of Bison, but the way this is going to work is we're going to just set a global variable that will hold the result of that. So that is here. So in our top program, we just literally assign the final return value to a global variable. And then in our main function, we just have a reference to that global variable, and then when we generate code, we just pass it in. So a minor difference. It's just using a global variable to hold it. I know you probably heard that never use global variables in C or everything, but in the compiler world or in these older tools, we do use global variables. But it's the same mechanism. Yeah, I mean it's a different mechanism, but the same effect. Questions? Other questions? Yeah.
We can just use a different internal mechanism because we're taking specification correct.
It's really an effect of Bison. It's because of Bison. It's the way Bison works. There are other parser generators that you don't have to that they will kind of have they won't use global variables basically. There are other parser generators that don't do it this way. Is that your question?
I was saying the reason you can just completely rewrite the electron parser or use Flex and Bison for the separator results and use essentially the same code generator because it's within the specification.
Because we're Because we're what?
Because the code generator is only cares about the input.
Yeah, that's exactly right. That's exactly right.
It's the same input.
So the question was, yeah, that's exactly right. So the code generator code is basically identical in this version of the toy compiler. And what your colleague was asking was, the reason for that is the reason for that because we have the same interface to the parser and the code generator. And that's exactly right. This interface is exactly the same. And this is another tip in software engineering is that when you define good interfaces, you can replace the implementation. This is kind of the classic object orientation notion. But you don't need object orientation to do that. You can do that with C code, you can do that with assembly. And as your fellow student pointed out, this interface stays exactly the same between the two parsers. You can think of the abstract syntax tree as one of the kind of core internal data structures that the internals of the front end of the parser at least use. And so that's exactly right. The output of the Bison parser that we made and the handwritten one is identical. In fact, it's specified in this ast.h, which once you get to write it, this is the file that defines the tree structure, and it's the same in both compilers. And Bison produces this exact same data structure. But yeah, that's a good question. Other questions on this? Other question on the toy compiler? One of the reasons that I have you do this toy compiler and just hand write it, which may seem like kind of busy work or something, is I find, at least in my kind of career, is that I would learn new languages by kind of hand typing example code in that language, and it seems like you're not really doing anything, but it does help you get over the notation. You know, I'm always kind of annoyed by notation, math notation. I like programming languages more than, say, math, because math is usually not formally defined. I mean, when it's taught, it's usually not formally defined. Computing, if you make a mistake in notation, the machines that are processing the notation won't work. And so you have to be extremely explicit in notation. And I find that you can learn that, you can get around the notation by just kind of turning it into muscle memory, you know, almost like learning a human language. You know, part of it is the accent and the vocabulary, things that are unrelated to the meaning of the language, that kind of stand in the way. And I think hopefully it'll also get you kind of used to the, you know, admittedly slightly esoteric syntax of the Bison system. There are other more modern parser generators that are a little less esoteric, you know, using money signs and curly braces like in C. And so hopefully by typing this out by hand, you'll just kind of get used to what the structure looks like. And then when we get to our much more complicated language, our SimpleC language, hopefully it'll be a little easier on your eyes, that you'll be a little more used to it. So just to give you kind of a preview of what the grammar for, hopefully not to scare you too much, this is the grammar file for SimpleC. It's, you know, a couple hundred lines, 274 lines. And so we have all the constructs from a subset of C, you know, types, type lists, statement lists, compound statements, if statements, while loops. And so there's a grammar construct for each one of these. And so you'll be going through and filling in the semantic actions to generate the parse tree for this language. And, you know, there are, you know, dozens of grammar constructs here. Whereas in the toy compiler, you know, there's only like 4. So it's a little easier to work with. All right, really good questions. Other questions? Okay, so yeah, I think we covered all of this. Okay, I think, so this is interesting to me. You know, I do research on like software operations and how that code works. So let me go into makefiles a little bit so you can see how these, you know, speaking of another kind of esoteric, older language, you can think of makefiles as a language for specifying build ordering and build rules. If we look at the makefile from our original toy compiler, I didn't really have time to talk about this too much. But yeah, it looks a little esoteric. But all this is doing is it's setting a variable that stores the list of C files in your project. That's all this statement does. The backslashes are just line breaks. It's getting another list of the source files, but replacing .c with .o. So, you know, now we've got a list of lexer.o, ast.o, etc. That's what object now holds, obj. This is just setting a variable that assigns the name of our output program. This is just saying that these are not actual files. These are fake targets. Don't worry about that too much. And so in the makefile, the first, so the way the syntax of this looks is that you've got, I forget what they're called, target, dependencies, and build rules. So the stuff before the semicolon is the thing you're trying to create. The stuff underneath of it is how you create it. And the stuff to the right of the target is what it depends on in order to build. So just to make a more concrete one, we could say the toy compiler depends on lexer.c, ast.c, parser.c, codegen.c, main.c, and in order to build it, you run this command, output toy, and then So this is totally a valid makefile for this toy compiler. You could just write this, and actually you could just only write that and have that be your makefile, a single line. And then when you run make, it'll say, oh, okay, I'm going to try to build the first symbol, it's toy, or the first rule, it's toy. If any of these have been changed since the last build, then I'm going to execute the build statement. So that's all the syntax of these makefiles does. And putting this into variables is just a way to do some clever tricks. So in this case, what make will do is this helps us do incremental compilation. So if you have a million-line program, 20 million-line program, and you don't want to have to recompile the whole thing every time you make a little change, in this case, so what make will do is it will look at all of these files and say, have they changed? If any of these files have changed, then it's going to rerun the build. And so if you've got a 20 million line program and you only changed one file, a 10-line file in there, the entire program is going to be recompiled. It could take you hours, potentially. So instead, what we'd rather do is say something like, okay, in order to build Lexer.o, only build it when Lexer.c changes. Actually, we don't even have to do that. We just say Lexer.c. So this is how you can build, or this is how you can just compile without linking. This is what we kind of talked about on lecture 2. This is how you can just do incremental compilation. You just compile each C file one at a time and then link them afterwards. So instead of having to write this for every single C file we have, just like the kind of insight that we can specify what we want to do in a specification language instead of having to hand implement repetitive code. Instead of writing this for every C file, makefile provides this pattern. So this money sign, fortunately kind of old-fashioned esoteric syntax, this is saying for any file that ends with .c, create a corresponding file that ends in .o, and do it by running the C compiler with these flags. And this esoteric symbol refers to the dependencies. That's all this means. So I'm not going to test you on this. You're not going to have to remember it. I just want to walk you through if you've ever seen these makefiles, because if you've ever had to build projects from the internet or have to do a little hacking in a makefile. That's all this is saying. These are just placeholder variables, just like in Bison, they use the money sign, or in Perl, some languages used to use money sign to refer to a variable. So that's all this is saying. This is saying for any C file, generate its .o file using this rule. And this statement, this is doing what effectively this does, but without having to build the entire project all at once. So this says to build the program, which is toy, and if I expand out, I can expand out the variables here for you. And then the object was this list that we created. Then run GCC with the output being toy, and then the input being all of these. So these are just more special variables that refer to the makefile rule itself. So pound ampersand is the target name, pound or money sign caret is the list of dependencies. So that's all this is doing. These are basically the same thing here. So the clever part about what make does is these don't have to be files. These can be other rules, or they can be files that are generated. And so this Lexer.o, in order for make to see whether it needs to, so it checks whether Lexer.o exists. If it doesn't, then it can look at the rule to generate Lexer.o. Kind of like this recursive nature of the makefile. It'll look for Lexer.o and say, all right, is that file there? If not, let me find the rule to make Lexer.o. So it'll look at the rule for Lexer.o. If it has been built but the C file changed, it'll be able to check whether it changed and rerun the build. Otherwise, it doesn't have to rebuild this anymore. And so if only one of these C files has changed, it'll only build that one C file and then just do the linking step, which is much faster than compiling 20 million lines of code. All right, any questions on this? I'm not going to test you on this. This is not like this is not like required to know. This is for your own sort of edification if you're ever dealing with system software or GitHub and dealing with like existing projects. Questions on this? Yeah.
How does it hold the state if it changed at the original source?
So the question is, how does it know whether it changed? It just looks at the timestamp from the file system. So that's it. So if you've ever seen a weird error like time skew detected or something in Makefiles, or if you've ever done any syncing, and you have two file systems that have different dates, slightly different dates, it'll say, hey, this was like modified in like the future or something, and it'll detect that and give you a warning. But it just literally looks at the timestamp. So if you like edit the file and make no changes, or you use the touch command, it'll recompile because it's just using the timestamp. Okay, so let me just show the, okay. So that's all this Makefile does. It just checks whether files have changed and then recompiles them. Okay, so here's the Makefile for our compiler built compiler, our one that uses parser generators. And you can see that it's pretty similar. It's quite close in most respects. So we have almost the same source files, we have the same object file, same toy. All the rules are the same actually, except there are two additional rules here. And so remember, the left-hand side is the thing we're trying to generate. The right-hand side is what it depends on, the source file that's used to generate it. And so this is how we can add the code generation step into our build rules. I want to say simply, but compared to the changes we'd have to make, it's a very small change to add our compilers into this process where we first generate C code first and then compile. And so all we do is we just add the rules for how we generate the Bison parser. So here's the file that we wrote, parser.y, and whenever it changes, we regenerate its output. So this is the command for running Bison to take parser.y and turn it into a C file. It just calls it parser.tab.c, which is why I call it, we could probably change the name, but this is how we insert code generation into our compiler process. And same thing for the lecture. Now we're not writing lecture.c, we're generating it from other code, and so it depends on these files being changed. And we just run this tool in order to generate lecture.c. Questions on this? Who finds this really interesting? Okay. All right, so let me wrap up these slides. So I think we already went through this. Yeah, okay. All right, so let's take a break. So you have a question? Yeah, go ahead. Yeah. Okay, come up and ask me. So let's take a break. Let's come back at 11:10, and we'll go from there. All right. Before we move on to the second lecture for today, just want to remind you, homework is up, so I've put up Toy Compiler 1 and Toy Compiler 2. Toy Compiler 1 is due next week, so remember it's just literally hand typing out, making the project, making sure your setup works, your virtual machine works, that you have somewhere to run your code. There may be a couple people I think who just didn't get Vagrant to work at all. I think Eustace might work. I haven't tried it. It'll build and run there. It seems to be using the same distribution. It seems to have the same similar architecture. But hopefully you've all got everything, all the kinks worked out, the virtual machine working. And so doing that Toy Compiler will sort of prove to you that your whole setup, your environment is working. Toy Compiler 2 for 2 weeks after that, or a week after that. I've kept putting up the homework. Any questions on the homework from last time? All right. Any questions at all about the toy compiler and parser generator? Yeah, sorry.
Are we supposed to compile it in the Baker machine?
You should, yeah. I mean, it might work on your machine. I don't know. It depends on what machine you have. It might work. But I just provide the virtual machine because that's what the graders are going to use. And yeah.
Do you have to like compile every file like one at a time, or like the main?
Just run make. Just run make. Yeah, if you just run make and you have the make tool installed, it'll use that make file to build the project for you. Other questions about the toy compiler projects? Okay, so hopefully those are straightforward. That'll really just make sure your whole system is set up. You got to get used to the syntax of the tools we're working with, the idea of having these multiple phases. Okay, so those projects will be due in a few weeks. And now I want to start getting into the language we're going to be really compiling in this class. So this is like the bulk of the class. The bulk of the grade is this, or not the bulk, but 48%, almost 50% of the grade is this compiler. And so for this lecture, all I want to do is just go through the language and just show you the language, get you used to what it looks like. Maybe show what parse trees look like, show what running the compiler looks like, and answer any questions you might have about it. And so we're going to go over an example of this. I'm going to give you an informal description of the language, and then we'll formalize it a bit using our compiler tools. We'll have a formal lexical and grammatical specification of it, and we'll have a sort of semi-formal definition of the semantics at some point in the class. Okay, so here's what SimpleC looks like. So it's basically a stripped down version of the C language. I just took like literally the C grammar and stripped out a lot of the more annoying stuff to deal with in parsing C and gave it what I think is a cleaner and simpler type declaration syntax. Parsing C declarations is super painful and complicated to deal with. So this main function will probably look, hopefully, pretty similar, pretty familiar to you in C. So you can still declare things by giving the type and putting the symbol name afterwards. We have pointers in our language, so we're going to learn how compilers actually generate code that does what the equivalent code in the assembly language is, and how we generate that. We've got integers and characters. But this type syntax is quite different from C. So in C, you have this kind of esoteric asterisk, and when you want to do double pointers and function pointers, the syntax is just, I always have to look it up. I can never remember what it is. So I use this kind of like sort of type theory, closer to type theory type definition. If you've ever seen generics, they use this kind of syntax. So if something's a pointer, you just say it's a pointer. If something's a function pointer, you say it's a function. You can have these like nested type constructors here. So this is a pointer to a function that returns a character and takes as input a pointer and a character. Anyway, we'll get into it more, but this is like what it looks like, the type specification. So it's much more verbose, but I think it's probably easier to read than the existing C type declarations. But otherwise, it's a stripped down version of C. Okay, oops, going the wrong way here. What? Oh, here we go. Something went wrong with, okay. All right, so expressions in the language, as I said, it's a subset of C. We've got the classic arithmetic operators. Give me 1 second, let me get a better pointer here. My Firefox crashed. Apologies for that. Give me 1 second. Wow, Firefox just crashed. Apologies for that. Okay, so sorry about that. So expressions, subset of C, we have the kind of classic arithmetic operators, addition, subtraction, multiplication, division. We also have pointers in this language. So what does ampersand do in C? Does anyone know? Yeah, gets you the address, gets you the reference. Star in C, what does star do in C? Dereference or multiplication or declaration. It has a lot of meanings, which is why grammar is important. You can't just look at the words because some words are overloaded. And array indices. So why do I lump together arrays with pointers? In C at least, yeah. They are pointers. An array in C is just a pointer to the first element. That's why arrays start with 0 in C. It's not that they're counting from 0, it's the offset from the first element. We've got relational operators, so we can do Boolean comparisons here. We've got Boolean, or we can get conditions. We have Boolean operators and an or, so just like in C. Statements, again, we have a subset of C. We only have 3 if statements, while loops, and assignment statements. Declarations, we use a subset of types in C. We use a very different syntax that I hope is clear. It makes clear the distinction between, in kind of the type theory world, or the type kind of compiler world, what they call primitive types, which are like leaves, the types that are built into the language, like int, char, those are the only 2 we have in this language, and compound types. Compound types are types that you create out of other types. So a function pointer type is a type that you construct out of the types of the arguments and the return value. A pointer type is a type that you construct out of the value being pointed to. So when you have a pointer to an int, you construct a new type, int pointer. There are other ways to construct types in languages like aliases, and they call them type defs in C. But these are the 3 we have in our language. So we can construct types for pointers, arrays, and functions in our language. So we can pass functions around effectively, or at least function pointers around in our language. So that's what we have in our language. Int and char, no other types, none of the precision stuff, double, yeah.
Does our language support double pointers?
Double pointers? The language specification does, yeah. Yeah, I can't remember whether I required it as part of the assignment. But yeah, the language specification definitely supports double infinite number of pointers. So you can, these compound types, as we'll see in the syntax, are nested. You can arbitrarily nest these types. So you can have a pointer to a function that takes a pointer, that takes a pointer, that takes an array, as much as you like. Actually generating the code to support that is a little bit of a different story, but yeah, the language specification in terms of its grammar can absolutely support nested type constructors. Yeah, good question. Okay, so here's an example of declarations. So just like in C, you can just put a primitive type name before the identifier you want to use for the variable. And just like in C, declarations and statements end with semicolon, or declarations end with semicolon. Here's an example of declaring a pointer. In C, you do int star y. I try to make the type construction aspect of this more obvious by, instead of parentheses, we use these little angle brackets to say we're doing a type constructor, or a pointer type constructor. So this is the same thing as saying int star y. It's a pointer to an integer value. So what kind of value is this y going to hold at runtime if it's a pointer to an integer? What's that? An address, yeah, exactly, an address. At the assembly level, everything just looks like a word, just bits. But by telling the compiler that this is an address, then we can check to make sure it's being used in the right way. This is how we declare an array in our language. So the array takes two type parameters. The first is the length of the array. The second is the type. So this is also a little different from C, because in C you don't have to declare the length of an array. Does anyone know in C what's the difference between declaring an array with a length and not? Did they teach this at all? Yeah. That's right, yeah. So if you specify the length, the memory gets allocated in the function local space. We'll see that when we get to how we actually generate code for functions, how functions are actually generated. That's actually pretty interesting, especially if you want to learn how the internals of the machine works. But the processor basically does not support functions directly. The compiler has to work together with the processor to create the function abstraction. So yeah, in our language, we don't just have arrays with no size. They're all basically compiler allocated. They're compile time allocated. If you want to have, actually I don't even know in our language I don't think we even support using, actually I can't remember in our language, but if you want to have an array of an arbitrary length or an undefined length, you can use a pointer to do that. Okay, so here's a case of what your fellow student was asking about. Can you have these nested, like double pointers? And so we support that in our language with nested compound type constructors. So here we've got a pointer to a pointer to a character. So at runtime, what type of value is going to be stored in the memory associated with this variable? An address. And if we dereference that address, that we go to the memory location, what type of value will be stored there? Another address. It's double pointer. And then if we dereference that, we follow that address and look up the value. What type should that be? A character. Okay, good. So double pointers. Okay, so for function definitions, we have a little bit of a much different syntax than in C. So in C, you put the return type first, and then you have your arguments on the right. In the old kind of KNR, Kernighan and Ritchie C, Kernighan and Ritchie C, you would have an even different syntax. I'm using this sort of like functional type syntax, where here's the syntax for function types. We put the arguments first in a tuple. So we put parentheses, a parenthesis with a comma delimited list of other type names. And then to specify the return type, we use this little ASCII art arrow to say, here's the return type. So this kind of comes from the type theory world a little bit, this notation. But this is how we specify function types in C. Questions on this? This sort of makes sense? Kind of looks a little graphical, kind of looks like an implication. If you have these types, that implies that you're going to get this type out. In SimpleC, we don't have void functions. All functions return something, and they have to have a return statement. This makes things a little easier when you're going to compile it. Questions on this at all? Function definitions? Yeah? It's not even supported in the grammar of the language. So a type is int char or a compound type. And in order to support void types, you have to say a keyword void to be syntactic in our language, or support a special function construct that doesn't have this arrow return type. So to make things a little simpler for compilation, everything has a return type, and the return types are restricted to int char or a compound type. So yeah, there's no void. You could certainly add it if you like. If you want to extend your language, by all means, you can add a void type. Just makes it a little easier when you're implementing the function. Yeah?
Sorry, to ask another question.
Yeah.
Could we simply specify that, say, if return type returns 0, and it can't ignore that?
Absolutely. Yeah, you could. So I think I don't have a way to call functions on their own. So this is kind of a good question. I'll take a quick aside since we're just going over the language. So in C, the reason you can call a void function like this, or call a function and just ignore its return value, is that in the C syntax, this, oh, sorry, you can't see it. Thank you. So okay, so let's take this call to function f here. And here's our function, and so you can just sort of ignore the return value. In C, there's a construct called an expression statement. And an expression statement syntax is an expression followed by a semicolon. So what that means is you can also say something like this in C. This is totally legal C to do. You take any expression and compute it and do nothing with it. Now, a cleverly written compiler will not bother computing this, but you can express this in C. You can also express things like this. You can say x star y. So what grammar construct is this, x star y, in C? Yeah.
It's a multiplication or declaring a variable.
Someone who knows C really well. So this is either a multiplication if x, so it's a multiplication if x and y are declared as variables, or it's a pointer declaration. So if x is a type, so I turned it into a type here with a type def. Yeah, so this is an ambiguity in the C grammar. Anyway, you don't need to know that. This is very nitty-gritty parsing stuff. But yeah, just to realize from the grammar point of view, the reason that you can call a function without saving its return value is that C allows for expression statements where you can just put an expression, and function calls are like saying the number 1 in C. You can just call them as part of your expression. So in our language, if I'm remembering my syntax, if I'm remembering my syntax correctly, or trusting what I said here, there is no expression statement. So if you want to call a function, you either have to do it in an if statement, a while statement, in a condition, or in an assignment statement. So you could create a variable, save the value, and then just not use it. But that's the best you can do to replicate a void function in our language. All this is really designed to make compiling it easier, so we don't have to support all the flexibility that C has. That's why I kind of designed it. That's why I designed it like this. All right, good questions. Other questions on functions? The return statement is always at the end of the function. So in C, you can put a return statement wherever you want. As the compiler writer, you have to know where the end of the function is. So trying to support all those return statements, and then support cases where you have a return statement in some paths but not in others. It's kind of annoying to deal with as a compiler writer. So as part of the syntax, the return statement is fixed at the end of the function. You can't just put it anywhere you want. It's not actually part of the set of statements in our language. There is no return statement in our language. It's part of the function definition itself in our language. And these are restrictions when you go to write the example programs or test for yourself. It's a little annoying to remember what the syntax is, but it's much, much easier to compile, I promise you. So here's an example of a function definition with our different type specification syntax. So kind of like in KNRC, like the old-fashioned C, we just say the function name and the names of the parameters. So we don't put any type information when we declare the name of the function, unlike in C. And then this little colon means here's the type. And then afterwards, the type must be a function type. So in the grammar, you can put any type you want, but when we go to check the type usage, it should be a function type. And so here is how this function type looks like in practice. So it says, I'm declaring a function that takes a single integer. So that's basically what gives A its type. And I'm returning an integer. So in order for this to be a correctly typed program, this return value type that I declare should match the return type that I actually use. So in this case, does it match? Is the return type of this function indeed an int? Who says yes, this is actually an int? Who says no? Okay. So yeah, we can conclude this because we know that multiplying it produces an int. All right, questions on this? Question on this example? Yeah.
Is the function type technically like a pointer itself, or is it just for syntax?
It depends on where it's used. So yeah, we'll see this when we get to type checking and code generation. The type itself doesn't necessarily imply how it's stored on the machine. So if you were declaring a variable to be a function type, the way we're going to implement that, the meaning of that is going to be function pointer. But we can also use that in the definition of a function. And so here it's not really a pointer. I mean, I guess it's all code is data in the architectures that we're compiling to. So when we generate this function, it's going to be at an address. So in some sense, it is kind of a pointer. But yeah, we'll see when we get to type checking and code generation how that works out. But yes, if you have a variable declared to be a function compound type, we're going to implement that using a pointer. Okay, so here's some more examples. Here's an example of having a function that has multiple arguments. Here's the name of the function. It takes two parameters. They're called A and B. And here's the type specification of that function. We use the function keyword. We give it a tuple that takes two types. The two types are int, comma delimited, and then we specify the return type with our arrow syntax. Okay, so here's another type. Well, that's, going off. Going off the screen a little bit. I changed the theme of this. But here's a more complicated example where we've got the name of our function, increment array. It takes three parameters, array, size, and amount. And in order to know the types of these, we look at the type specification. So colon means here's the type. We use the function keyword and then a tuple that has to have three types in it. The first one is a pointer to an int. The second one is an int for size. The third one is an int for amount. And then our return value, which is off the screen because of my new theme, is a pointer to an int. So that's the type specification for a function that takes an array, takes the size, takes the amount to increment, and then increments every element in the array and returns the array. Yeah?
So I know, I don't know if you saw this, but I know that an array is a pointer, but if it has its own syntax for an array, why would it then say that array type?
Oh yeah, good question. I mean, this is. I think I did this program so that because, I think I just chose this one to have a pointer to the array instead of passing the whole value of the array. Yeah. So I guess in this language, I should say I guess I designed it. In this language, you can do both. You can do either, like in C. Yeah, I think in C you can also can you pass an entire array in C? Yes, you can, right? You can pass the whole array. So this, I just chose to do it this way for this example. So another difference from C is that we have a mandatory main function. So every program in SimpleC has. Oh yeah, got a question. Oh no, it's not. good call. Good. Yeah, you found a bug in my example. It's not. So this is a broken program. Good catch. Yeah, it should be incrementing high for a correct program that doesn't loop forever. Good catch. I'll I'll fix that. All right, so another difference, simple, yeah, go ahead. There's no, dynamic, so just like in C, dynamic memory, you mean like allocating an array at runtime, like with malloc? Is that what you mean, or are you talking about dynamic typing? Yeah, so you can, so we'll get into that when we look at how functions work, but malloc is just a function that you call. And so there's nothing you need to support in the type system or the design of the language in order to support malloc, because malloc is just a function that somebody wrote. And because it just returns a pointer, you can support it in this language. So you can support calling malloc in this language as well. And I can't remember if I assigned it as part of the, I'm revising the assignments for the project. But technically speaking, because we're compiling to Intel C, or Intel x86, and we're going to be binary compatible with Linux, the Linux OS, we can actually call malloc from this language. We'll be able to link to the standard C library, call malloc, and generate, at runtime, get dynamically allocated memory, and be able to use it in our language. Yeah.
So we would, for example, be able to resize the array.
Yeah. Any functions you can call in C. I can't remember if I actually will put it. I'll see if maybe I should put it as we'll see if it's part of the assignment. If it's too much, I want to gauge if it's like too much to deal with. But technically speaking, you can compile this to be binary compatible with the Linux ABI, and then link it with the C standard library and call whatever functions you want. Printf, even though we don't have. You could do printf. You'd have to encode you'd have to have a character string. You should be able to call printf, malloc, realloc. You can call all of those. The type system supports pointers, so we can support malloc. Now, whether we can, so we'd have to make a wrapper function. We'd have to make like a C stub for ourselves to wrap it. We'll get to that when we actually get to code generation. But you wouldn't be able to call malloc directly because I think, actually, could you call malloc directly? You might be able to call malloc directly, but we can make a wrapper, basically a C extension for our language where we call out to malloc. I think that's how I do print. I think this version of I have several versions of this compiler I did for the class, so I can't remember which I did. But you totally could just link with a C function, and in that C function you can call malloc or whatever function you want, even if this type system doesn't support those calls. Like if you call it a function with a struct or something, you don't have that in this type system. This is like language interoperability stuff that probably shouldn't go into right now. But yeah, we totally could call malloc and have dynamically allocated memory here. Other questions? All right, so there's there's a mandatory main function here, so we're not supporting separate compilation or anything. This is just make stuff easier to compile. So this is actually part of the grammar of the language, where we force all programs to have main in it. We have control over the grammar specification, so we can design this language however we like. We can make the return value part of the definition. We can make the main part of the program. So we're not going to specify the int arg stuff, int argc, the argv. That's all going to be built in. So the way I think I designed this version of the compiler is that the only input comes from the command line, and the only output is the return code of the main function. That there's no print statements or anything. Although if we do the language interoperability stuff, we could print as well. But the minimal compiler we have here is just the main function is the input and output of the program. Okay, so here's the example we saw before. And let's go through it, the meaning of this in SimpleC. So we're declaring a single global variable x. We're declaring a single function f that takes two parameters called a and b. They have this type. The first one's a pointer to an int. The second one is a character, and it returns a character. The function has to have a return statement or a return syntax at the end of it. Dereferences a, and casts b to an integer, adds a and b together, adds the dereference value of a. So basically takes the ASCII value of b and adds whatever the pointed value is. And this main function declares three variables here. One is a pointer. This is finding the memory address. This is assigning the character. I don't actually call the function here, but I probably should. And this returns the character C. So in the core language, there's no printing or anything. If we're not doing any language interoperation with C, then the only way to do input and output to SimpleC programs is through the command line arguments and through the return value. So on the command line, every program in the Unix world returns some value in its main function. Oh my God, crashed. This is so every program in C returns a value, even if you don't call return. It's part of the Unix standard to return a value. So normally when you think of the output of the program, you think about printing or file I/O. These are just warnings. So this is what happens when I run the program. But if you want to see the return value of main, you can do that in Bash using, again, a money sign prefixed special variable, money sign question mark. And this will tell you what the return value of that program was. So you can think of running a program in Linux as calling a function. And that function has inputs to it, the argc and argv. And it also has a return value because it's a function call like any other function call. So if we change that return value, and let me get rid of the warnings. If we change this return value to something else, like lucky13, and we run hello, you'll see that if I ask the operating system what the output, ask the shell what the output of the last command was, it'll give me that return value. So this is kind of like the true output of a C program. It's like the return value of the main function. If you ever wondered why you had to do 0 or why you had to do return at all, this is why. It's just part of the kind of Unix specification, or at least the C standard library specification. And so to make things simple, to not have to do like language interoperability or deal with file I/O, the test programs I give you are going to check this return value that we give from the program. That way you don't have to worry about like file I/O and stuff. And there'll be instructions when you actually go to we get to actually the code generation part. There'll be instructions on how to use this, how to use this money sign question mark. So you don't have to remember it. Yeah.
I noticed that in the example function, you pass the character to an integer.
Yeah.
And return an integer as a character.
Oh yeah, I did do that. So this will depend on the type specification of the language. So in C, you can do this stuff because not just because characters are integers, everything is an integer at the machine representation level, or they're all binary bits. But C will actually detect uses of different types and do casting for you. It's called type coercion. And after we do, so in the second phase of our compiler, we're going to specify the types, the type specification of this language, and we'll actually check to make sure types are being used. And we'll go over what the actual type specification of our language is then. Yeah.
You didn't actually call your function.
Yeah, I didn't call the function in this example. This was just to illustrate the syntax of it. We can go over semantics once we actually start. doing the type checking and running these, and code generation and actually running these programs. This is just for illustration. Other questions about SimpleC language? Yeah.
So what is the default value
So it depends on the definition of the language. So in C, it's undefined. It's undefined behavior to use a variable before you define it. And the compiler does not, the compiler is not required to check this for you. So this is the case, really gets down to like language design and how the compiler is written. So C is designed to have very fast compilation, very easy compilation. And so if you use things in an undefined way, like say you read an array out of its bounds, in terms of the C specification, it just says, well, hey, that's on you. That's not my fault. You shouldn't use the language like that. That's not valid C. But unlike syntax, where we have a very formal way to automatically check whether we followed the correct syntax, this is a little bit harder to do for other properties of the language, like did you read an array out of bounds? This gets into the notion of decidability, Turing completeness, Turing machines. If you take like discrete or discrete 2, they'll talk about decidability. Basically, at the end of the day, if you have something that's equivalent to a Turing machine, which physical machines, arguably are not because they have finite state. But if we model them as this Turing machine, then it's not possible to write a compiler or any tool that will figure out what the result of that computation is at compile time. So questions like, is there a null pointer error? Is there an out-of-bounds memory read? It's not possible, it's not decidable to write a tool that will figure that out for any possible input program. And so the way the C compiler handles this is it just says, if you have undefined behavior, I will generate whatever I like. And usually that's the easiest thing. Like if you write code that has a memory out-of-bounds read, the compiler will just generate code that does the out-of-bounds read, even though that's not valid C. So in our language, we're going to do the same thing. It's the same thing for using a variable before it's been defined. I think the way I have my current compiler written is it just doesn't initialize the variables in memory. It'll just use whatever memory was there before, whatever values were in memory before, just like many C compilers do. Some C compilers do zero it out for you, but I don't think the C standard requires that to happen. Long answer to a simple question, but this is a language design question. We'll talk about this more when we get into the generation of our code, the semantic definition of our language. But the C compiler, leaves lots of things undefined and leaves it to the user or additional tools to help you find whether you've made those, use that undefined language. All right, good questions. Other questions about SimpleC specification? Yeah.
Do you allow variable length arrays?
Variable length arrays, only through pointers, only as a pointer. There's no syntax, so you can conceivably add new syntax that says, here's how you can change change the size of an array. You could add that to the language. You could make a function in your standard library that takes an array of one size and outputs an array of another size.
I just mean
Yeah.
could you have like a non-constant expression when you define an array type, like have an integer that's like changed?
Can you give me an example of the code you mean? So
Like array and is like a non-constant expression.
Oh, you mean can this syntax here be anything other than a constant?
Yeah.
Not in my language, not in this language, not in SimpleC. But there are such languages. I mean, there's a whole huge body of work on type systems, and there's a class of type systems called dependent type systems, where the type constructors themselves can contain program variables from the language. So you could have a program like this where you have some program variable X, and you actually use it to construct other type names. This is way, way outside of the scope, not something I even work on. But people do conceive of such type systems. They end up being undecidable in general, depending on the design of it, because if you were trying to do a compile time type checking, you'd have to be able to basically solve the runtime values of all variables. But yeah, and our language is not going to do this. It's not going to have variable length. I think GCC supports these, right? C99 supports them. There are some ways to support this. I think there are ways to actually support this in C. But no, we're not going to have to do that. They're annoying. I think they're pretty annoying to support, if I remember right. Other questions about the language? So all this is really designed to make compilation easy, or easier. Compiler writing is like hard generally, I think. And so I've tried to make compromises in the language that are designed to make it, because I wrote the compilers too. I wrote these. I don't just make you write it. I write them myself first, and I want to make it easy for me too. So these are compromises in the language that are easier for writing the compiler. Other questions about the language? So I had this, before this crashed, I had an example of this, I think. So here's another kind of similar example. I have a couple functions defined. I've got some declarations here, some expressions. So the first project that you're going to work on will, oh no, it's not this one. Sorry, I had this set up in the Vagrant machine, and then this terminal crashed. Okay, I think I put it here. Yeah. Okay, so this was the class example, the class we had, the example we just showed on the board. And so for your first project, you're just going to be doing syntax analysis, just going to be getting the syntax tree of this, which is why I was kind of sloppy in the actual meaning of it. It's not a very useful program. And you're basically just going to fill in the parser.y program, and this will be the output of your program. It'll be this kind of nice ASCII art tree output. And so this is what this will look like. We'll talk about this more next week when we actually get into trees and syntax analysis. But otherwise, that's the SimpleC language. That's the language we're going to be compiling. Yeah?
So this language has no structs, right?
No structs.
So to implement a tree, you do an array, you use index manipulation?
Oh, so we're implementing it in C. So we do have, so this is the mind warping part about writing compilers, is that we have our input language, we have our output language, and we have the language we're writing the compiler in. So fortunately, we're not writing the compiler in SimpleC. That might be a lot more painful. We're writing it in C. So when we implement the language, we have access to all of what C has. Yeah. Now, if you wanted to bootstrap your compiler, which means you write the compiler for the language in the language that you have. So if you look at like the C compiler source code, it's written in C. So you have this bootstrapping problem of, well, how did you compile that first if you never had a C compiler? You have to write in assembly first. But fortunately, we're not going to be writing it in SimpleC. We have structs in C. Other questions? All right, so there's a nice talk. You can look at the notes if you want to see this, about language design from kind of an eminent scholar in programming languages. He was involved in Scheme and Java. Kind of a cute, interesting talk about how languages are designed, some of these decisions around the language. But otherwise, that's all I have for today. Just wanted to introduce you to SimpleC. And have a good weekend. We'll see you next time.